In this video, we are going to do an example of a sort of harder problem that involves work. So we're still using that work is force times distance formula, but in fact we're going to have a handful of other formulas that come into play as we're working on this. Now, I've also got the camera and camera picture set up, which I can't actually see, but supposedly you can see in the video. And I have Vanna White waiting off here on the side, who's going to do some of the drawings for us at the whiteboard as we walk through solving this problem. So the example is written here, again, on the worksheet that I posted to eLearning for you, but I've got it up on the screen as well so you can see it. So what we have is a very fun application, fun in my opinion, I suppose, of work involving calculus. So what we're going to be doing is drinking a tequila sunrise today. So we've come up with some measurements. We have this conical shaped glass. It's got a radius of 5 centimeters, a height of 10 centimeters, and it's got a mixture in it, a liquid, whose density at its height is given by this formula, e to the minus y grams per centimeter cubed. All that is to say is that the further down in the glass you are, the denser your drink is. Something layered like a tequila sunrise would have that property. And because we're very fancy, we're drinking a tequila sunrise, we're going to be drinking our drink through a straw today. So we're going to empty the contents of the glass through a hole that happens to hover above the glass at a height of 14 centimeters. Not really hovering there, it's part of a straw, which is going to be our mechanism for drinking this. And we want to figure out how hard we're working when we're emptying the contents of the glass in this way. So here's where Vanna is going to come in. Vanna is going to draw a picture of the situation because all good problems in math start with a picture. Vanna? So here Vanna is drawing our cone, which is our glass. And Vanna is going to draw the straw in. Now this information isn't really in the problem, but we do have to make some assumptions about how the straw is sitting in the glass. So our straw is going to assume, we're going to assume our straw is in the middle of the cone, and that our straw goes all the way down to the bottom of the cone. So now Vanna, can you step off that way? So yeah, I guess they can see this way. So we've got just a picture of the situation. We've got our glass, we've got our straw in there, and we've got all our measurements, the radius of the cone, the height of the glass, and then the height of the straw written in centimeters here. So that's our first step. So we draw a picture of this situation. And the next thing that we want to do is we want to sort of put this glass and the straw on an axis, because what is important is work is force times distance. Force here is going to be something we'll have to figure out, but what matters is your distance from where, sort of the distance away from a slice of this glass to where it's exiting, where we're done working, which is through the top of that straw. So we're going to put in a slice, as Vanna has done here. We're going to introduce a variable y, which represents the height that you are in the glass. And we're going to take a look at kind of the contents of the glass that exists at that height, which is going to be a tiny little slice of our glass. Now I think that so the first question on our worksheet is to draw a picture of the situation. The second question is, what is the basic shape of this slice? So remember that we're working with volumes here, and we haven't drawn it in, but our slice has a teeny, teeny, tiny thickness of height, almost like the thickness of a sheet of paper or the thickness of the marker, very teeny, tiny. And then when we slice this glass, we can see that we're getting something that's circular, that really has a teeny, tiny amount of height, which we're going to call dy. So the shape that we're getting here is that of a cylinder. So we've got a little bit of a cylinder. And the third question on the sheet is what's the volume of the slice? Well, since we know the shape, and we know the shape is a cylinder, we know the formula for the volume of a cylinder, which is going to be pi times the radius of the cylinder squared multiplied by the height of the cylinder. So our job now is to translate those variables, those arbitrary variables, r's and h's, into things that involve our variable that we're using in the problem, which is a y. Now the height of the glass, I said out loud, is this teeny tiny amount of height, this very minuscule thickness. That's the quantity we've been calling dy. So we can sub in dy for h, and then the volume is pi times the radius squared dy. But the question is, what is the radius of that green cylinder that we have drawn in the picture? So to figure that out, that's actually perhaps the hardest part of this problem, is figuring out that radius. And to figure it out, we're going to use similar triangles. So what triangles do we have in that picture? We have the triangle that's representing the radius of the original glass, the height of the original glass, and then the sort of diagonal side of that original glass. And then we have another relevant triangle in this situation, hybrid of those two words. We have the height of the liquid that we're looking at, which is a height of y, and then we have the radius at that particular height, which is the radius of the cylinder we're looking for. So we have this triangle which has this sort of height y and radius r. And r is the variable we're interested in solving for, but because these triangles are similar, we have this nice proportion that we can set up. 10 over y is equal to 5 over r, and we can cross multiply to solve for r in this equation. So when we cross multiply, we solve and we figure out that whatever that radius is just half of the height that you're at, and we plug that in for r to get that our formula for the volume of that green slice is given by pi, quantity y over 2 squared, multiplied by dy. Very nice. Thank you, Vanna. So Vanna's going to erase the proportion just to give us a little bit more room. We're going to proceed on with answering our questions. The very next question on the worksheet is, what is the mass of the slice? So remember that our formula for mass is just that the mass is the density of the liquid times the volume of the liquid. And luckily, this problem was set up to find these parts as we go along. The volume was found in part 3. So if we sub in for volume, we just have the thing that we had in part 3, pi times y over 2 quantity squared times dy. That's our volume, answer from part 3. And for us, there's not much work to do to find the density. In fact, the density was given to us in the problem. The density is e to the minus y when we're at height y. So that's the answer for part 4. Mass is density times volume, and we just sub in for those things. Moving on for number 5 here. Number 5, what is the force exerted to lift the slice? Well, at this teeny tiny amount of height, we're using that the force is constant, so we're using that force is just mass times the force of gravity. Remember, we're dealing with grams and sort of SI units here, so we have to factor in the force of gravity, unlike in the last example. And normally, gravity is given to us as 9.8 meters per second squared. The only difficulty in this situation is that we are dealing with centimeters, so we have to do a little bit of a conversion here. We have 9.8 meters per second squared, and we need to convert meters to centimeters. So we need to use this fact that there are 100 centimeters in a meter to do this little equation. And we get that the force of gravity dealing with the units we're working with is 980 centimeters per second squared. So we'll sub that in for little g, which is our force of gravity. And for mass, we'll substitute in the answer from the part we just got. Part 4 was figuring out what the mass is, e to the minus y. We're doing some simplification here. We're grouping our constants together. E to the minus y, pi over 4, y squared dy, and then all multiplied by 980. Very good. So that's part 5. And the very last part of this problem is just to set up an integral that computes the work that is needed in order to figure out the total amount of work required to drain the drink. So we're going to need an integral sign to do this integral. We're going to use force, that work is force times distance. So we're going to need force, which is what we computed in part 5. Let's take what Vanna's done here is taken all the constants and put them on the outside of the integral so that they don't confuse us. And we need force, which is e to the minus y. What's left is the y squared dy. And what's left to go on the inside of the integral to be the integrand is the distance required, the distance that we need to travel if we're this slice of volume that's existing at height y. So for this, Vanna's going to come back to our picture. And we're going to try and figure out, if you are this volume of liquid existing at height y, how far do you need to travel in order to have completed this, this journey to compute your work. So if you're sitting here at height y, all of that liquid needs to travel first down to the bottom of the straw, and then it needs to get sucked all the way up through the straw, and then we'll be finished working at that height when we've completed our journey. So it seems to me that you have to first travel those y units down to get to the bottom of the straw, and then you have to travel the total distance of the straw before the work has been finished to drink that layer. And so as we have written up on the board, that distance that something at height y needs to travel is its own height, y, and then the 14 units it needs to travel up the straw. So to complete our integral, we've got all those constants from the force outside the integral. Then we're looking at e to the minus y squared, times the quantity 14 plus y, or y plus 14, all multiplied by the dy. And the very last thing that's missing from our integral is we need to figure out when we're going to start counting, or the bounds on the integral. So we need to figure out when we're going to start counting these units of distance and when we're going to stop counting these units of distance. So for that, we're going to discretize this entire cone that we have in our picture. We're going to start at the very bottom of the cone, which is y is equal to 0. And we'll have added everything up when we reach the top of the cone, which is at a height of 10 centimeters. And all together, let's put a nice big box around that answer. That's our answer for part 6, and the answer for how much work would be required to empty the contents of this glass through the straw. 980 pi over 4 times the integral from 0 to 10, e to the minus y squared, times y plus 14 dy. Thank you, Vanna.